Good evening, everyone. I would like to begin by acknowledging the traditional owners of the land upon which we meet, the Wurundjeri people of the Kulin Nation, and acknowledge elders past, present, and emerging, and extended respect to all Indigenous people present here this evening. I would also like to recognize that we are on unceded land and that Indigenous people have been custodians of these lands and waterways for Australia for more than 60,000 years, and they were our first teachers and educators. As we near the end of the second month of spring, we acknowledge the Wurundjeri people's long-standing relationship with the caring of the lands and waterways. The Kulin Nation lived and continues to live their lives according to their own markings of the changing seasons. According to the Kulin people, there are 7 seasons, each reflecting the movements of the stars and the change in the weather, which align with the life cycle of plants and animals. Currently, we are in Purnit, tadpole season, and on the cusp of entering grass flowering season. Tadpole season is characterized by new life everywhere, and as the change of a season, it brings a second wave of flowering, particularly for trees. One flowering plant of tadpole season, known as myrnong or yam daisy, is the inspiration behind the yellow, most often used for our Faculty of Education identifier. So welcome, everyone, to the very special occasion, to the 5th David Clarke Memorial Lecture. It's great to have all of you with us tonight and to see such a lively audience here. And thank you for all of you who have come to hear our special guest presenter, Professor Tytler. For those of you who I haven't met yet, my name is Marek, and I'm professor here at the University of Melbourne and Dean of the Faculty of Education. Tonight's lecture commemorates the life and work of our valued and much admired colleague, Professor David Clarke. I would like to take this opportunity to acknowledge David's wife, Sharon, as well as 2 of David's brothers, Mike and John, and to offer to all of you special and warm welcome. Thank you all for being here tonight. I extend this welcome also to Associate Professor Peter White, and who is joining us in support of her husband, our guest speaker, Professor Tytler. And may I also thank in advance Dr. Maurizio Toscano. Where are you, Maurizio? Here, thank you. Who will be facilitating the Q&A following tonight's presentation, as well as the co-chairs of the International Community for Classroom Research, ICCR, Professor Jan van Driel, Dr. Carmel Mesiti, and Dr. Esther Chan for delivering the vote of thanks. You're all here, right? Excellent, here you are. Those of you who knew Professor David Clarke describe him as an extraordinary, generous educator and friend who took great pleasure in the success of those around him. Dali Lenoir, a former Emmet student, recently shared the following. I still remember David Clarke with immense fondness. He was my very first professor in the Master of Education, and I shall never forget the moment I pitched my thesis synopsis to him. The whole class seemed to fall silent as he leaned forward, his eyes gleaming with that unmistakable enthusiasm, curiosity, and openness that defined him. He engaged with my theme as though embarking on an intellectual adventure, unafraid of where new ideas might lead, as if tracing the mathematical meanderings of mystery and discovery itself. That spirit of fearless inquiry still lives with those he inspired. What a beautiful statement. While his talents were broad, one that transcends them all was his natural ability to connect people and colleagues and to bring them all together, which is what this lecture is also about. For nearly 40 years, David's research focused on capturing the complexity of classroom practice through international video-based studies across more than 20 countries. He joined the University of Melbourne's Faculty of Education in 1994, became a professor in 2004, and served until his passing in 2020. His work advanced educational research for critical self-reflection, innovative designs, and sophisticated tools for studying, teaching, and learning worldwide. In 2002, David founded the International Center for Classroom Research, specializing in video-based classroom studies, particularly in mathematics education. The center's global research network remains a vibrant testament to his legacy. David's influence remains through his prolific scholarship, 12 books, over 50 chapters, 70 journal articles, 90 conference papers, and the supervision of more than 20 doctoral students. His flagship research project, the Learner's Perspective Study, compared mathematics classroom in 16 countries, and became one of the most cited projects in the field. In recognition of his impact, room 417 in the Kwon Lee Dao building, where we currently are, was renamed David Clarke's Research Classroom, a lasting tribute to his exceptional contribution to educational research and most fitting way to honor his memory. In fact, when I walked past the other evening, there were students in there studying and in lively debate, which was great to see. Personally, I met David through U21 meetings and was always impressed by his kind nature, sharp intellect and deep sense of collaboration, respect and healthy academic disagreements. I often think back to our vivid debates at the AERA Dean's meetings, where he would so passionately argue for and advocate on behalf of education. We all owe David a great deal, and I'm sure almost all of us here in the room have our own David story. So with deep respect, we honor David's legacy through our lecture this evening. I would now also like to take the opportunity to introduce our guest speaker, Professor Russell Tytler, and to tell you about his notable career to date. Russell Tytler is Deakin Distinguished Professor and Chair in Science Education at Deakin University in Melbourne. Along with Russell's background in lecturing and teaching physics, he has been influential in developing the science curricula in Australia and is involved in a range of Department of Education, teacher, professional learning initiatives. Russell is widely published and has been a chief investigator on a range of research projects, including current projects investigating interdisciplinary mathematics and science pedagogy, representing contemporary science research and development in schools to support and informed climate change education, and directing an innovative program for the Victorian Department of Education and Training for out-of-field teachers of science and mathematics. That's a lot, Russell. He's a member of the Science Expert Group for PISA 2015 and 2025 and represents the OECD on the International STEM Skills Forum. But that's not all. Russell was also deputy chair of an influential STEM country comparisons project for the Australian Council of Learned Academies and is a fellow of the Academy of Social Sciences in Australia. With David Clarke's work building understanding of the types of engagement involved when students learn mathematics, and Professor Tytler's extensive research and writing on student learning and reasoning in science, it is more fitting that Russell delivers this special memorial lecture. So please join me in offering a warm welcome to Professor Russell Tytler to deliver the 2025 David Clarke Memorial Lecture, exploring new understandings of teaching and learning science and maths. Welcome, Russell.
Thanks, Marek, for those kind words. That's great that I can be here tonight. Actually, I'm really pleased to be able to, particularly at this event, to be honouring David, who was a good friend and a colleague over a number of projects. Just before kicking off, I would just like to echo Marek's words about acknowledging the land of the Wurundjeri people and that we are here on unceded lands and love to honour their elders past, present and emerging. David, a lot of what you said, Marek, is very much echoing what my memory of David was. In fact, I think that gleam of enthusiasm, I've got this picture of David and you can see it there in that photograph. And I coincided with David over many projects and events here in Melbourne, but also overseas at a number of conferences. And it was always great to be overseas with David. If you happen to be on his invitation list for restaurants, he knew the best restaurants in every city, and he would always know the local lie of the local land. I can remember once I was in Gothenburg with him for a few weeks. We were both visiting professors there and staying at the same place. And so at breakfast, he would come down and he'd say, "I've got a new problem for you, Russell." And he would pose a logical problem that we would then chew over through to when we had to go off and do our professing work. David also was a great friend of Deakin. He would come to our Contemporary Approaches to Research symposium regularly, and it was just great to have him there because there are not many people who can have that incisive kind of critique, if you like, of work, but in a really supportive way. And he was always very generous in his commentary and questioning of our colleagues. So I'm very pleased to be here to honour his legacy. One of the things that I remember was very influential for me with David was his theoretical position about complementary accounts of learning. And this drove a lot of his work around, for instance, the project on international languages in which to describe teaching, each one of which would bring different perspectives on the learning task and the learning practices. And I remember we were both involved in the special ARC research initiative, The Science of Learning, and one of his very early lectures there was here in Melbourne. He talked about the fact that we can't understand learning through one account. The Science of Learning Research Centre was really charged with looking at the science of learning across neuroscience, across cognitive science and across education. And David argued quite forcefully and I think compellingly that understanding learning in the classroom could not be reduced to the movement of neurons, that we had to actually find ways of bridging across those different areas of scholarly endeavour, and that each account would bring different insights that we need to align. And so that idea ran through a lot of his work there. And so the question really, and this is part of the content of what I want to talk about, was how do you actually marry these different perspectives, and in what ways do we see them as being related? And there's been a lot of critique of some of the work of neuroscience being overly quickly translated into classroom practices, because we're dealing with really complex interactions between people and ideas and cultural traditions when we're dealing in classrooms. And certainly neuroscience can tell us a lot about this, but then there's this question about what are the translation mechanisms that enable us to actually make sense of this and to get some productive discussions going across those fields. And there was a very famous paper back in, I think, 2006, perhaps, titled "A Bridge Too Far," which really was asking the question, how much does neuroscience contribute to understandings about how teachers should behave in the classroom? And so that's part of the question we were dealing with there. And in that paper, the argument was that cognitive science needed to be the bridge between the two, and you always had to move across those areas. In fact, echoing David's concerns, you've got quite a bit of work coming out of the Science of Learning Research Centre by Jareth Horvath and Donna, who looked at this issue of translation and really put up this model, for instance, of different levels at which you can understand these phenomena, from the basic cellular processes, the physics of neuronal transfer, up through looking at organs and the way they contributed to our, which would be visual and sense organs, of course, to organisms, and then to complex interactions in the classroom. And their analysis and proposition echoed what David was talking about, that these are incommensurate levels of theoretical understanding, but we need to see or work out ways they can align and inform each other. And this notion of emergent properties is what Jared talked about with that increasing complexity up at the classroom level. And so basically in this talk I want to offer, if you like, a critique of too easy a translation up these levels of complexity in these different disciplines, each of which can bring valuable insights, but we need to be thinking about the different vocabularies, the forms of evidence and paradigms that each of them brings to this. So as part of perhaps a word of warning, I know at one stage within the Science of Learning Centre we had one of our key neuroscientists there who was actually was vociferously, if you like, holding out the proposition that we'll never understand learning until we understand the neurons. And we had quite a few lively debates about, well, you know, what is missing inevitably from understanding neuronal processes, and how do they relate, and what is the value? In fact, this is partly a question of status as well, because when we talk about the science of learning, there are questions of status involved. And this book, which I've read recently, The Blind Spot, makes the argument that if we're talking about science and its processes, it's very heavily dependent on, or one of its major characteristics is this way it reduces reality into measurable components and abstract ideas that can break down problems into parts, and that's the power of science. But the argument of this book is that with all of that, we've got to remember that these abstractions are always models that we can use to predict what happens with the world and to control. But in terms of human experience, there's so much more than that. There are emergent properties, there are increasing recognition of complexity theory. And they talk about this, if you like, era of reductionism, that there's a presumption that once we know the science abstractions, that's all we need to know about learning or about reality. Whereas in fact, if you think about something like the problem of consciousness, how does the mind emerge from the brain? And how do we think about, or is it possible to think through the tools of science about the mind and imagination and all those higher level terms that come to, we talk about our fundamental human experience? How does that relate to the abstractions of science that look at the movement of neuronal impulses? And the other error that they point out is the error of smallness, that in fact we tend to assume that if we go down to these micro phenomena, that somehow they are more fundamental and at a more fundamental explanatory level. And so again, I come back to David's point that we have incommensurate theories, each of which gives us separate but to some extent compatible, hopefully, views about the nature of learning. And Bruno Latour talks about, he was a great scholar of the science process, talks about how science in establishing explanations really values moving further and further away from humans in presenting abstractions in order to chase objectivity, and that the higher status theories are those that are the most abstract from human experience. So what does that have to do with learning? And that's what I really want to come back to. A few months ago, there was a Dean's lecture here by Guy Claxton, and he made the point, and he was critiquing what I'm going to talk about in a minute, the emergence of a particular view of the science of learning in Australia and, in fact, New Zealand and overseas. And he talked about the need to, rather than talk about the science of learning, we should talk about the sciences of learnings. And I want to take up that theme, thinking about really what sciences are we talking about, and can we look at different levels of scientific phenomena or in fact educational phenomena that give us different insights into that. And also the learnings, it talks about the multiple purposes of of schooling and learning. And I think this is key. We've really got to keep our minds sharply focused on the broader purposes of education and be very aware, if you like, and suspicious of reducing it to particular measures and particular ways of looking at learning. So let's have a look at this question of public policy and how it relates to the science of learning. At the moment, the Victorian Education Department has a new Victorian teaching and learning model, which looks like this. It's broken down into elements of teaching which look really convincing, and in fact there's a lot of wisdom involved in that. But if you look at the sort of language that it uses, they are really very strongly, if you like, promoting a particular view of learning that's about information, knowledge and memory, attention, retention, mastery and application. They're all dealing with information processing models, and they're dealing with the use of memory to remember things and how to do things. And I would argue, and many people are arguing, that this is in fact the imposition of a very particular science, cognitive science around learning, and it's a very narrow one. But let's have a look. It's based pretty much, and this is coming out of federal moves in AERO, the Australian Evidence Research Organisation, that is looking at a particular view about learning, looking at it in terms of restrictions on working memory. And the model we've got here is that in fact information comes in by attention of an individual into working memory, which is then processed and then deposited in long-term memory. But the problem is that working memory has limited capacity, and so what is presumed from this or argued from this is that we need to teach explicitly and very carefully in small chunks of information. And if you look at some of the work coming out of this, for instance, this is coming out of one of AERO's worksheets. It's about the problem of learning about atoms, but atoms consist of smallness, it's one part of the concept, a nucleus and electrons, and so we need to really chunk that to build up a picture and then store it in long-term memory, and then it's available with less memory space in there. And so it's all about compartmentalising learning and breaking it down so that it can be appropriately dealt with, perceived and remembered there. There's a lot of very good research goes behind this, but the argument is, and the argument is put in many places, is that this model of learning is based on very particular measures of learning outcomes, and they tend to be algorithmic. They tend to involve students being able to actually manipulate abstract quantities. And again, I come back to the blind spot problem, that we really need to be suspicious when we think of the abstractions of science, of maths, as the reality that needs to be learned, and divorced from the experience of what it is to be human and what it is to really value this knowledge, what it is to feel, have a disposition to use that knowledge. These things are part of the broader purpose of education, and that I'm going to illustrate some of the things we've been doing with that. This book here argues, for instance, that, and it's consistent with the work of a scholar, Pickering, in The Mangle of Practice is the book he's very well known for, who argues that in fact, if you're building a science theory, you've got to both build the theory and build the phenomena, or arrange the phenomena of the world in such ways as your theory makes sense. And it's this dual, if you like, he calls about the dance of agency between the materials you're looking at and the theories you're developing. And so if you've got a particular theory about working memory in this case, it's best shown by restricting your attention to the very particular sorts of knowledge that helps make sense of that. And so there's a problem that what it tends to drive you with towards is a particular version of the brain and of the mind and of learning, and particular sorts of knowledge that support this. And so it's not that any of this is wrong, it's just that we've got to be very suspicious about the narrowness that we might find it leads us into. So what I want to do now is get on to things I like talking about, and that is the work we've been doing with teachers and students around, I think, wider purposes of education. And I'm thinking of science mainly, but also mathematics. And there are 4 areas here that I think certainly our research tries to touch on that I think are really fundamental. The first is this notion that disciplinary knowledge or learning of disciplines involves induction into the multimodal reasoning practices of the discipline through sign systems that are multimodal in nature. And so rather than thinking of learning as learning an abstract quantity that can be then manipulated and repeated in an exam, we're learning really the practices of that discipline and the reasoning tools, if you like, that are inherently multimodal. And allied with that is what is often called the turn to practice. That in fact, in thinking about classroom practices, to actually expand our notion of learning as the, if you like, acquisition of something, of disciplinary knowledge, to really thinking about students practicing and learning to practice the discipline and how that knowledge is used. And also the notion that learning is also about feelings and habits, that part of the values implied or underpinning disciplines are these habits of how you think about reasoning, how you develop curiosity, what things you develop curiosity about. And we know that there's a lot of research that shows that students can learn a lot of really good science in schools in terms of their test passing, and they never use it again after they leave school. And so this question of disposition and the question of student agency, what do students feel confident and are they committed to using the knowledge that they are acquiring? So the theoretical perspective that we've been using, and this is a book that came out in 2013, is that of looking at multimodal representations and how they are used within disciplines. This was not a new idea, but I think we took it further than most and started to really look at the students' generation of representations to both explore and explain phenomena. And this is a very recent ARC that Marek referred to, looking at interdisciplinary science and maths in the primary school. And this is a pedagogical model that really looks at really students or teacher posing representational challenges where students are asked to represent phenomena in some ways, but to orient them first. And I think this is important because I think often, we always call this a guided inquiry approach, but often inquiry is presented as students being just given problems and left to kind of sort things out. This orientation is key, I think, and we've worked with teachers on this. And then out of those representations that students produce, you build consensus. So the teacher is basically orchestrating, both introducing, stimulating, orchestrating student work. And underpinning this is we use the work of Charles Sanders Peirce a lot. To Peirce's view, he's one of the fathers of semiotics, is that we understand the world, objects in the world, through creating signs through which we can perceive them and talk about them, and that so that the referent in the world will be the physical object, the representation or representamen or sign is what you produce, and separate from that is the meaning you make of the sign. And what I've got up there is just a whole lot of snaps to illustrate what we mean by representation. This was from a grade 2 fast plants unit where students actually grew and measured plant growth and plant reproduction over the life cycle of a brassica plant that has a very quick life cycle, been specially bred. It's a model plant, if you like. And you can see there the rich range of kind of representations or signs that in fact our students were exposed to or generated, and from diagrams to linear kind of representation of plant growth tables, and finally graphs. And those graphs were produced by those grade 2 students to represent, that one is to represent the whole class. A group decided that was their project, and they generated all of the data and plotted that at grade 2 level. And this was actually orchestrated pretty much by Peter, who's sitting there in the front row. Let's jump to illustrate what we are talking about. Let's jump to this Year 8 unit on force. One of the things about the learning of force, it features a lot in the conceptual change literature, in that students come to force with an everyday notion that force is a property of the body, and it's very hard to shift them to the notion, a Newtonian notion of force, that it's an external, if you like, effect that creates a change in motion. So to start this sequence, Lynn, the teacher in this case, asked them what they would do with a lump of plasticine if they were giving it a nasty change its shape, and so they produced a lot of those words on the left. And so that's the everyday language around which we think about force. And then she asked them to group them into two types of force, a bit ambiguous really, but pushes or pulls. And so they were grouped into those two categories. And we talk about this as an interlanguage, taking each student's everyday language and experience and starting to move them towards accumulating a more precise language of force. There was a lot of gesture went on around this. Then they were asked to change their lump of plasticine in 4 moves, and then write down what they would do, what they did to that plasticine, and then hand the recipe, if you like, to another student to see if they could duplicate it. So there was a test. And so there's some examples of what students did. Some of them looked like a recipe book, others had diagrams. And in the discussion, which is part of the third stage of that primary school model I showed you before, the class agreed that the most clarity was achieved when there were diagrams there. So they were establishing the need for visual representations to do that. But then it so happened in this class, no one came up with the idea of which way you're pushing. And so she led a brief discussion about how that could be improved and came up or suggested arrows. And then they went back and all modified their descriptions with arrows. So they were learning to develop a sign system, a representational system, which is fundamental to any analysis of force. As someone who's taught physics at Year 12 and beyond will attest to. And so what, in a sense, they were being presented with was what we call an ontological gap. It's this shift from the idea of force as a property of an object to the idea of force as something that happens on it is a change in ontology. It's a change in the status of the term force. It's a change in the way of seeing the world with that concept. And so from that, the class went on to look at how to represent large, small forces, twisting forces. How would you represent how to roll the plasticine or squash it? And then there was continual discussion around this, comparison, and so on. And that then led into a sequence of increasing sophistication of force representations, calibration of a force measure, reaction forces, and forces on parachutes and so on. And so really they were using that sign system to look at a range of objects and extending the language of force. At the end of that sequence, we interviewed the teachers, and it's interesting to see the sort of things they referred to there. What they talked about the pleasures of developing ideas with the students rather than rather than delivering. I now realise I was sort of coming in via the second or third floor. What they'd done in the past, encouraged by the textbook, was to give the abstractions, but never really built it from where kids were at. And so there's this. This is what the blind spot is talking about. The abstractions replaced the richer reality of how those abstractions are developed and situated, and referring to the science debates and conversations. And so I suppose just to summarise the lessons from that it was really the grounding of force concepts in everyday language, the representational challenges to set up a language that enabled that ontological gap to be breached, continual encouragement of student representation. We call this, there's a lot of interest in epistemic agency, students being able to make decisions and own their ideas. There's this notion of epistemic climate, the idea of collaborative building of ideas, the extension of the language, and the movement between multimodal representations. Okay, so really that example, you'll see there, it didn't start with the teacher telling, right? It was an invitation, but it was very strongly modelled and orchestrated by the teacher. Perhaps a problem that's closer to the sort of problems that cognitive load theory deals with is this one in year 11 class that Lam Pham, who did a PhD with us a few years ago, worked with the teacher to develop this sequence. And the problem was, what happens when you mix two solutions of different concentration? How do you work out, or in fact, you can have various versions of that problem, but this is the sort of equation that students had to deal with, and that was notoriously difficult. In order to solve that, I'm not quite sure how that would be dealt with in the traditional cognitive load type approach, but it would be to do with breaking down the problem into bits. But what Lam did in working with the teacher was to make what I think of as a sideways move. Instead of dealing with the abstraction directly, what they did was to get the students to do an experiment where they progressively diluted a concentration, a solution of concentrated permanganate, I think that is, solution. And so that you're arranging the world to make visible this notion of concentration. It's really a marker, if you like, to do that. And then challenging the students to think about, at a submicroscopic level, what that might look like. And so they're constructing a visual representation about what underpins that reduction in concentration. Then Lam, and we talked about this quite a bit, one of the problems in these types of problem is that you've got to keep separate in your head the amount of solute and the amount of solvent. You've got to have those two things separate. And so he invented this cross and portion model, where a cross represents one mole of a particular amount of the solute, and the square, the portion, is the number of litres, is 1 litre. And so you can represent what's happening as you mix solutions by tracking that. And then that can then lead to the symbolic representation. And the students were challenged to start to work with and make sense of this cross and portion model. And he tracked the way they used it and reasoned with the model. And they became quite adept. Some of the students became quite adept at it. But it did, the teachers were really impressed. It did substantially improve their mathematical or use of the mathematical equation. So what we argue is that in fact, you can't understand a mathematical equation like that without thinking about the meanings underpinning it and about what each bit represents. And it's through that movement between the mathematics and the kind of mental models, if you like, that need to be established and represented. You in fact, making the point that a mental model doesn't appear out of nowhere. It's actually the establishment of perhaps visual diagrams or embodied sort of actions there. And so the notion of schema needs to really think about that range of multimodal signs. And within that sequence, you've got explicitness of the teaching, and you've got inquiry in terms of students being challenged to invent and to reason using those inventions. I'm going to go through this a bit quickly, actually, but this notion of transduction has really interested us in the last couple of years, and it's really a term that's used. It's a term. It really means translation, but translation across different modes. How do you actually make links across from one mode to another, visual mode to a mathematical mode to a material mode? And it comes with the notion that when we talk about a concept in science or maths, that they're ultimately semiotic hybrids. It's like that the concept of the mole was a hybrid of all of those different visual and modelling images that I showed you before. And so what do we do to support transduction? And that making of meaning across modes in terms of Peircean theory comes about by different sign functions. So if you look at this model of the heart, for instance, we know it can link to a real heart in an iconic sense, in that it's shaped like a heart, it has 4 chambers, it's got a structural similarity. Or an indexical function, when we start to use that model of the diagram of the heart to start looking at the flow of blood and the movement of the valves, you're using the diagram to index what actually happens in the heart itself. And so it has a reasoning function, and the symbolic function is when you've got things like words which have no iconic similarity but are culturally agreed conventions. And so let's have a look at, and I wanted to come to this because it's got another photo of David in it, it's work we did here in this building in the Science of Learning classroom. And that's the David in the control room with the control bits and the sort of view out into the classroom. And this was really powerful. We did a number of studies here with this classroom, and you've got you've got a view on the left there from above. You can hear what students are saying, and you can also look into what's happening from the side. So you've got a lot of power in data collection. And this was a challenge for Year 7 students. It wasn't a teaching sequence. It was really looking at reasoning and how students might reason to make sense. In this case, these 2 students had the problem that Lisa sees that the sun is higher in the sky at midday in summer than it is in winter. How can we explain that to someone using drawings or so on? And so students started making a diagram. They thought, okay, it has to do with the orbit of the sun, of the Earth around the sun, and it's got a tilt, so they knew that much. And then they had this model globe and torch which they were played with, and it was really interesting. They were very active in using and manipulating the model of the globe and the torch looking at where the light was shining, talking about, oh, well, you can see the torch clearer from there. If I turn the globe around, I can see it more clearly from here. And so they achieved this sort of somewhat imprecise, but really got quite excited about the fact that in winter the Earth or Australia was further around the corner from the torch. And what their problem was that they had to then translate that into the drawing, which involves quite a transduction move. I'm sort of running out of time, so I won't play you the video, but it really shows the back and forward and problem solving that they were engaged in. And well, while I'm talking, you can watch the video. You can see how both the reasoning and the talk switches between the two boys reasonably quickly, and they're manipulating. So there's this embodied sort of modelling that's going on there, which they then need to translate into in the drawing. There they had a struggle, and we learned quite a bit about the way that they dealt with that transduction. For instance, I'm going to... there's some of the language. Yeah, I know I'm saying this is because it's pointing right at it. It seems to sound more than it does. There's a lot of metaphorical language there around that sort of gesturing and physical embodiment. You've got a lot of spontaneous adjustment and the creation of signs. They were very inventive in that. And then in translating it, you can see how they took the 3D model and worked with the diagram. And so that process of diagramming, they were actually actively involved in moving between the two and manipulating the two there. And so I guess we theorised, Joseph's here is one of the authors on the paper, we theorised quite a bit about diagramming as the creation of meaning and reasoning, and that notion of disciplinary learning as being consisting of the need to move across those modes and some of the challenges of transduction in doing this. But you see again the excitement of all of that for the students. So if we just cut back to cognitive load theory, this is a paper by Stu Sepp, who's been at some of our events, which looks at, rather than attention just being to do with information, it's really looking at visuospatial, auditory and embodied foci. It's a much more complex embodied sort of notion of working memory, which really makes it a much more complex task to think about the cognitive load on and how that's managed in a task. And so we're starting to get, with this version of working memory, much closer to our semiotic perspective about the multimodal nature of learning. And we've become quite interested in this notion of embodiment. We ran a festival of embodiment last... there we go. I'm out of time. And you can see how embodiment actually gives you lots of... really has lots of echoes in arts-based practices, for instance. It has lots of echoes. And in fact, there's a lot of translation of neuroscience understandings about the body and learning that one can draw on to do this. So I guess I'm going to just, this was a mathematical example for the mathematicians there, but maybe those three examples are enough. I'll to sum up. That in fact, what I'm arguing is that deeper disciplinary knowledge and practice can't be reduced to manipulating abstractions. It's got to actually deal with the underpinning sign systems, including the body, visual sign systems and so on, that we know from decades of research into conceptual change that in fact you can the deep disciplinary learning involves really the creation of new realities by science. A lot of science is counterintuitive, a lot of maths is counterintuitive, that needs to be established. And direct teaching just doesn't really do the job of dealing with those fundamental, deeper shifts. It's good at manipulation of equations, of abstractions, but for the deeper understandings which produce or confer flexibility in learning, then we've got to go deeper. And finally, this notion of epistemic climate, the idea of collaborative creation of knowledge, epistemic agency, where students are given some control over their learning, are really fundamental. And within that shift between explicit and inquiry teaching, it's not as if one should come before the other or as if there's a right way of doing it. You've really got to... it needs to be a matter of judgment of the teacher and what's appropriate for particular forms of knowledge and particular students. Thank you.
Thank you, Russell. I'll just ask you to stay here. So
that's fine.
Thank you so much. My name is Maurizio Toscano. I'm a senior lecturer in science education here at the Faculty of Education. And it really is a great honour, even though I'm just facilitating the question and answer session. It is really a great honour to stand next to Russell as he delivers the address honouring David Clarke. Because it occurred to me that one thing that we're worried about is the tyranny of small things, which is what Russell was alluding to. But I think what we really should be concerned about is the tyranny of small minds and the lack of imagination. So it seems fitting that Russell's very kindly continued David's tradition of approaching small things with imagination and with originality and innovation. And I think that's, I guess, what you were saying in your presentation was to go beyond the small things. And I just thought it reminded me of our, at the cusp of the Industrial Revolution, William Blake writing that we should, to see a world in a grain of sand and a heaven in a wildflower, hold infinity in the palm of your hand and eternity in an hour. And I think the eternity and infinity speaks to the pluralism and the endless imagination that you're calling for in your own research. So thank you so much, Russ, for that wonderful presentation. We have time for questions, about 10 minutes or so. We have a microphone roving around so that given this is being recorded, so that we can preserve your questions and answers for posterity. But please wait for the microphone to come along so that everyone can hear you as well. And if you could kindly introduce yourself, that would be lovely too. So if anyone has any questions or comments to make, yes, just thank you.
Hi, thank you very much. That was a fascinating talk. I'm Josh from the Teaching and Learning Lab in the Faculty of Engineering and IT. I'm wondering about the connection that seems to be almost assumed or implicit between a theory of how learning works and a necessary or inevitable conclusion as to how teaching should work as a result of that. That seemed paired, and I don't know if that's what is intended to come across.
That's a good question, and a lot of it depends. I mean, in terms of how learning should work and how teaching should work, a lot of it depends on the teacher as such and the judgments that you make. And I'd also make the point that there are fundamental kind of aspects of how learning works, but individual learners will bring very different dispositions and so on. So the teacher judgment is always crucial, I think, for dealing with particular students. How learning works, certainly, as you heard, we take a very much a semiotic perspective on that in fact disciplinary learning involves the production of science systems and students inducted into how to do that. Of course, there are so many ways of introducing science systems, and so there's no. I don't think there's a particular pedagogy that flows from that. More, it's a set of, if you like, principles. For instance, I've got some really nice footage of a teacher lecturing at year 12 physics students, where he's really carefully looking at transduction across, in this case, electric circuits and equations. So that's one thing. In our research, we tend to push towards this notion of the turn to practice. And so I think there we're pushing for students engaged in the reasoning process from the start. So I guess what I'm saying is there are learning principles, there are individuals, and there are purposes, and they all interact. And so I think there's a complex line to be drawn between a particular teacher's practice and what we know about learning principles. Yeah.
I think there was a question, two rows back. Thank you.
Thank you. My name is Dr. Sarah Rosen. I'm an evolutionary anthropologist, actually from the University of Durham in the UK. So I've come a long way. Thank you so much. I was really thrilled to hear you mention embodied teaching and embodiment, because that's an interest of mine from the context of human evolution and teaching human evolution through evidence that we see in our own bodies. And I'm curious if your experience with embodied teaching, is the data retention better in students? Like what are the outcomes when using an embodied method that you've seen in your research thus far? And is there a clear path forward for using it in classrooms?
We haven't, we're just starting down this track, let me say, with embodiment. And for instance, in that festival of embodiment, we were really just looking at exploring the notion. And certainly from an individual perspective, you can see immediately how powerful it is. We've been doing some work with looking at students at grade 6 level on ray optics, for instance. And part of our interest was triggered by the fact that we could see how the action of the body in tracing light or in sort of positioning the body to see images was just so central to that notion. And so we worked with the teacher, and the teacher really took it up as to make that part of her practice in the classroom. I mean, beyond that, there have been certainly studies in neuroscience that show greater retention and greater understanding of physical principles, for instance, of force or rotation, I think is the study I'm thinking of, when a person is actually involved themselves in it. And I know, I mean, even just thinking about my own experience, sometimes when you're teaching, students kind of keep their hands behind their back, but those that are really engaged and reasoning often will be using their bodies. And so I think there's a heap of informal kind of support for this, but and some formal studies, yeah.
Question at the front, thank you. Oh, just we'll wait for the microphone.
Thank you. Sorry, Hugh Kingsley, Educationalist. Thank you for a really inspiring lecture. One thing that stood out to me, excuse me, I think one of the early slides you presented, you were constructively critical of the government or the model that came up. And to me, it seems that governments are typically reactive. Now, given that we're in an era of rapid change with AI and so forth, how can we bring ideas like yours forward so that we are in real time competitive?
Did you say competitive or? With the rest of the world. Oh, with the rest of the world, yeah. Well, I mean, I think part of the political problem is that we've ceded our measures of learning to standardised tests. That's become a very big thing. And so I think the attraction of the science of learning that's reflected in the Victorian departments, I think is a reflection of the fact that that's the area that CLT and the sort of principles that it espouses, the practice and direct teaching excel in. So we've got a kind of a tight binding between what I think is a narrow view of learning and a narrow view of purposes. And so I would hang my hat on the fact that we really need to have flexible learners. We need to have people who are really engaged. And we know there's a bit of a crisis in retention of maths and science students. We would like more to go on, at least either into STEM professions or as citizens who are cognizant of and respectful of science and mathematics interpretation. And so I think really what we've got to do is lift our sides and argue that way. And actually, Peter and I were talking about a colleague from Denmark yesterday who was talking about this move towards explicit teaching as having been ascendant in Denmark for 10 years or up to 10 years ago. But there's been a pushback there coming out of particularly some Norwegian work, and the nature of the pushback was built around this idea of purposes and really talking about fundamental purposes rather than simply exam results. So I think flexibility of learners and purposes, I think that argument needs to be loud and clear, I think.
We have time for just one more question. Thank you.
My ex-student, Sam, just alerted me to the fact that I taught her years back.
Yes, thank you, Prof. That was calling you Prof is a little bit.
Yeah, she knew me in a different persona.
It'll take some getting used to, but I am here as an alumna of the uni, a recently retired bench scientist, and the line about science risking becoming divorced from what it is to be human, I felt that. But I think you've made a very good case for the power of enabling students to sort of develop this mental model, and it seems that just drawing is a very simple and yet really powerful way to come to grips with what can be some like really anti-sense concepts. I wonder, have you identified, or do you anticipate, or have you documented and studied the caveats? Are there any caveats or potential pitfalls with that? I'm thinking in particular. I'm thinking of the model of the atom that I was introduced to in primary school, which has got the nucleus and then electrons whizzing around on their very highly defined roller coaster tracks, and, which obviously later you come to learn that's really not how it works at all, but probably introductions to the difference between pi and sigma bonding to grade 4 students not appropriate. So how do you play off those two tensions against sort of what is appropriate for the age and what may not necessarily be sort of an accurate reflection of the real concept that you are trying to teach?
There's a lot to say about that question. Thank you. I think the question of appropriateness of content goes beyond drawing, of course. I mean, I know in primary education we've had these debates about whether you should introduce particles when it may introduce misconceptions about what a particle is, but you just nicely illustrated that there's no one thing that an atom is. There are lots of models, and the models become more sophisticated as you go up the scale, if you like. And I think to me, part of the power of what we've been doing with students is to introduce the science systems as conventions that are really powerful. But we found, for instance, when we get students to draw and discuss, like we did in the force example, for instance, there's no one absolutely right way to draw an arrow for force. There are conventions. And so we found as our students went up into secondary school that the teachers there were saying they were quite noticeable in the way they would really be critical of textbooks or question representations, and so they'd realise the not the well, the revisable nature, I suppose, of science concepts. So I think that needs to be built in. And to me, that notion of the atom and the electron is useful at a level because, you know, it enables you to do certain things. You know, the idea of a particle is useful for younger students at a level of talking about evaporation, for instance. But it starts to become a little bit difficult once you start to talk about chemical change. You know, so I think it's a matter of growing sophistication and realisation that these things have different levels of modelling. Yeah.
I'd like to now call on the co-leads of the International Centre for Classroom Research for the vote of thanks. And while they make their way up to the podium, I'd like you to please thank Russell for
Good evening, everyone. My name is Esther Chan, and I'm one of the co-leaders of the International Community for Classroom Research Hub, which is a continuation of the research network that David started more than 30 years ago. I have the honour to give the vote of thanks to our honourable speaker and colleague, Professor Russell Tytler, tonight. David and Russell have been long-time colleagues, and they complemented each other in many ways through their work in mathematics education and in science education. David's work in the classroom mainly or generally focused more on discourse, while Russell's focused a lot more on semiotics and representation. Each of them offered us fascinating insights into how teaching and learning works in the classroom. David always liked the idea of complementarity. It forces people to think about how we harmonize divergent perspectives. It makes us consider how we can resolve seemingly contradictory or polarized ideas. Rather than focusing on a single perspective, tonight, Russell encourages us to think about how multiple perspectives can complement each other in the curriculum and in the classroom to support teaching and learning. On behalf of my fellow ICCR Hub co-leaders, Professor Jan van Driel and Dr. Carmel Mesiti, and the ICCR Hub community and our audience, I would like to express our gratitude to Russell for your thought-provoking talk. What a very fitting way to commemorate and celebrate the work of David. Thank you so much. Last but not least, I'd like to also thank Yvette McDermott and the events team for organising tonight's event. Now, may I invite the Dean back to the lectern for his closing remarks.
Thank you so much, Russell. Thank you so much, colleagues, friends. What a wonderful evening, and thank you so much for being here. This concludes the 2025 David Clarke Memorial Lecture. Thank you for joining us here tonight and to honour the life and work of Professor David Clarke. Thank you so much, and set travels back home.